All right, students, going to try another one here from our mirrors. Again, it's based upon the law of reflection, but this is working again with mirrors. This is going to be a concave mirror. So number 18 basically says repeat the one I just did, number 17. So if you saw that video, great. But I'm going to repeat this one and then now do it for number 18. And the difference is we have a concave one. All right. So the image, well, maybe I should start with the object. So this is the height of the object, okay? And I'm going to then put it 30 away, so let's call that 30. And I'm going to make a mirror curved this way now. And I hope I didn't curve it too much here, because we want the focal length, so this is going to be distance of object. And so the focal length is about twice that. So here's the focal length. So the focal length here, F, is 60. And we're asked to, first of all, draw the rays, and then from that, use geometry to find out where is the location of the image and what is its magnification. So let's draw the same two rays that we did in number 17. Here, the ray that would come across the top would hit the mirror, bounce, and go through the focal point. And the second ray we like to draw, and this one's a little harder on this one, we like to say draw the one that leaves the object, goes through the focal point, and hits the mirror. But when you're in front of the focal point, that doesn't really work. We got to change our phrase to say draw the one that's going to hit the mirror at the same angle as if it was coming from the focal point. So maybe I'll make like a little dotted line, because it doesn't really come from here. The light actually leaves the object, but it leaves the object at an angle from the focal point. And we like that one because we know the one that comes through the focal point and hits the mirror then bounces off and goes parallel. And so somebody standing over here would get these two rays, this one here and this one here, and they would go and trace them in their mind back to where they meet. And so it looks like they don't actually meet because we hit the mirror, but they have the appearance of coming from somewhere back here. Right there. So that's where the tip of that arrowhead would appear to be coming from for this person standing over here, because the light was redirected. The light is a little controlling, or the mirror controlled the light to give it the appearance of coming from right here. So the bottom of the arrowhead would still look like here, and so this right here then would now be what we would call the height of our image. That's how big this thing would be. And so it magnifies it. This is the mirror that I think I said in the lecture is the more interesting one, because we can make things bigger or smaller with it. We can make them upside down or right side up, whereas the other mirror, the convex mirror, was kind of boring. It always made things smaller and right side up. But this one, if you get it in front of the focal point, things can look bigger. So that's what we have here. So I guess this is the first part of it. It says draw the ray diagram. So I did it, and this is where it appears to do. And now it says go through your geometry and figure out the magnification and figure out the location. All right. So let me draw my colored pins again. And for those of you who saw the video before, I drew in green, so I guess I kind of want to match the same color. This was number 17. I drew the one that had the actual objects in it in green. So to kind of match that, let me do this. The one that has the actual object would be right here. Okay. And if you kind of imagine transferring the height of the image right here to this mirror. Now again, I know it's curved a little bit, so my picture exaggerates how much these mirrors are curved. But I'm just going to kind of put that a straight vertical line and then make a big green triangle here. And so I'm hoping you see two green triangles here, a big green one and then one inside of it, a small green one. They are similar. And so if this right here is the height of the image and this is the height of the object, I would say the height of the image is to the object. So this height is to that height. As this length, so that's the focal length, is to this length. Now this length would actually be this whole focal length minus object distance. So it would be focal length minus object distance. Now, notice that that is not quite the same formula that we did on 17. See, that had a plus sign because it was over here on the other side. And now we have a minus sign. So that's why I said in the last problem, and I want to say here, that you should write these down and have them ready. Because even though I'm going through all these steps, this is really what was covered in the lecture. So you don't need to do it for the homework, and you definitely don't want to take the time during the test. You want to be able to jump on these formulas, okay? Plus, then, that means you don't have to do the geometry. And I know in the past, students have kind of been a little rusty on their geometry, if you will. They're like, oh, no. So that's why I thought I'd go through it here a second time. All right. Now, let's do a blue one. And again, just comparing it to the last one. The blue one I made before had the image in it. And so let me do that here. So if I make a blue triangle with the image in it, so here's the image, and it extends all the way out here. So this is a big blue triangle, okay. And if I then use the height of the object and just kind of move it over to the location of the mirror, I'll put it like that. Okay. And I'm hoping, again, you can see two triangles here, one inside the other. There's this big blue triangle and then this smaller triangle inside of it. Because if we were to then say, well, those two triangles, since they're inside, they share that angle, they're similar triangles, then the height of this is to this, so the height of the image is to the height of the object. So the height of the image is to the height of the object as this distance. Now, let's talk about this distance. I didn't label it here, but this out here would be distance of image. So the image is virtual. It's over here on this side of the mirror, and so it would be the focal length plus image distance over this length, which is just the focal length. Now, let me point out again, that's not quite the same formula we got back in 17 when we did the convex mirror. Again, because they were on different sides. So we got a minus sign, and this time we get a plus sign. That's why I say it's probably good just to put this in your notes, put a box around it, write on it. In this case, it would be concave mirror. This would be the set of valid equations. Last time, I guess I just put convex and I didn't put mirror. But I do want to put mirror because in the next chapter, we're going to do this geometry with lenses. And you're going to see that the mathematics for the concave mirror is different or is the same as the convex lens. Now, I also should be careful because I didn't say it in 17, but 17, the convex mirror is kind of boring. It always does the same thing. So I could just say this is always true for the convex mirror as well as the concave lens. There's nothing really more to say about it, because if I have an object, no matter where I place it, the geometry works out the same. But the concave mirror is kind of interesting because we could have a scenario that's a little different when the object is beyond the focal point, okay? And then another situation when it's beyond the radius of curvature. So I need to put here, this is true for the concave mirror, but if the object distance is less than the focal. And so that's true for this case. Maybe back in 17, I should just put always. There's only one case. But there's 4 of these equations. 3 of them come from the concave mirror, because you can be at 3 different positions and get different geometries. Or actually the second and the third one are really kind of the same. So you might want to think of those as just a second one. But the point is that this one has at least 2, 3, depending on how you look at it, different positions you can get in different equations, whereas this one only has 1. Okay? And so I won't do them all now. Maybe someone will ask a question about those other ones, but go ahead and make sure you look at the notes and you have all those written down. But I do want to put here, make sure you write if the object distance is less than the focal length, okay? Because once we get beyond the focal point, we'd see that the rays met on the other side. The geometry looks very different, okay? So be careful with it. All right, so now let's answer this. And just like before, maybe I'll grab my green one. I can calculate this first. They asked for the magnification. And the magnification really is the height of the image to the object. So it's this. So you can just say it's the focal length, which is 60, over the focal length minus the object distance, which is the 30, which then makes 60 over 30, which makes a magnification of 2. So unlike number 17, where we added them and got a magnification of 2/3, so it was smaller, this one we subtracted down here, and so we get a magnification of 2. Okay. Now we can use that, and I'll change pens to the blue one here, because then we know this ratio. This is the magnification, so we know that number is a 2. And then if we put in the 60 here, we can then solve for what is the image location. That's the last part of this problem. And so now I can cross multiply. That becomes 120. That becomes 60 plus DI. Subtract 60 from each of them, and you get an image distance of 60. All right. Hope that helped. Enjoy.